What's up?
So we're set up for
8.9 number 51.
So I think I'm just asking, like, I think I can take this limit as we gotta split it up into two limits,
Yeah.
and then from there, like dealing with the square root of 4 minus p squared, you can either do a trigonometric substitution, or you can just factor that and do a u sub.
Okay. So yes, we've got integral from -2 to 2 of this guy. And I think that what's really hard about improper integrals sometimes is that they're like hidden, right? And this is one of those where like at -2 and 2, this thing isn't so good, right? Yeah. And so you need to be careful, around the edges, so to speak. That said, is this thing symmetric? So like if you plug in +1, what do you get on the bottom? Square root of 3. If you plug in -1, what do you get on the bottom? Square root of 3. So this thing, whatever it's doing to the right of 0, it's doing to the left of 0. So if I wanted to, I could simplify it right off the bat by just saying this is 2 times the integral from 0 to 2 of dp over square root 4 minus p squared. And now we don't have to break it up into 2 anymore, although we could. Okay. So the two bad spots on this one are -2 and 2, right? So yeah, you could kind of think about it as, okay, we could let the sides go to -2, go to 2. But since it's doing the same thing in both cases on either side of 0, I'll just double splitting it up once. And now we can write this one as a limit. So this is 2 limit as b goes to 2 from the, I suppose, left, correct? Integral from 0 to 2 of dp over square root 4 minus p squared. Okay, and then the question is, what's the antiderivative of 1 over the square root of 4 minus p squared? Now, one thing we could do is we could do a trig substitution. Do we need to?
You can also do a factor, I think. It's a weird factor, but you can.
Okay. Okay, here's a question. Oh, yeah.
Isn't that the derivative of like cosine, either cosine or sine?
Right. Okay. So instead of asking what is that antiderivative, tell me this. What's the derivative of sine inverse of x? Does anybody, yeah.
It's 1 over the square root of, 1 minus x squared.
Yeah, that's right. That's pretty darn close to what we have right there. So the question is, how do you change it to be right? Well, I just know this from experience. If you wanted to, I could substitute here and make like p be equal to 2u or something. So when it's squared, it's 4u, and then I could factor out the 4, yada, yada, yada. But another way of thinking about it would be, I believe that the answer is that it's just x over the square root of this thing. But let's check to be sure, because I haven't done this in a little while. So it's 1 over square root of 1 minus that thing, x over 2, squared, times the derivative of what's inside, which is 1 over 2. Now, if I took that 2 and put it inside the square root, it would be a 4. So this would be 1 over, I bring this in as a 4, that becomes a 4. minus, and then I get 4 on top and 4 on bottom, so they cancel, and I just get x squared. So do you see that the derivative of this guy is here? So the antiderivative of this guy is here. So this one is just 2, limit as b goes to 2 from the left of, so the antiderivative of 1 over square root of 4 minus p squared is just sine inverse of p over 2 evaluated from 0. Oh, I wrote something wrong right here. That's a b. Sorry. From 0 to b. Correct? Okay, now we can plug it in. We get 2, limit as b goes to 2 from the left of, if I plug in b, I get sine inverse of b over 2. And if I plug in 0, I get sine inverse of 0 over 2, which is otherwise known as 0. Okay, so now I'm ready to plug in that b is going to 2 from the left. But if b is going to 2, 2 over 2 is 1. So really I'm just saying sine inverse of 1. Or in other words, sine of what angle gives me 1? Pi over 2. So this guy, so I still have this 2 out here. And then I get sine of, when I plug this in, this is 1. Sine inverse of 1 is pi over 2 minus sine inverse of 0. In other words, sine of what gives me 0? And that would be 0. And so I just get 2 times pi over 2. And that is pi. Yeah.
So, but if I wanted to,
Yes.
I could have done the quadratic formula and then use that to split it up and then did a u sub.
Okay, where do you want to use the quadratic formula? Here?
Yeah.
Well, okay, so what would happen if you did the quadratic formula?
Oh,
For-
that wouldn't work. because
You
then
get
you'd
2
have
and
to-
minus
it
2.
wouldn't be squared by itself. It would, yeah, that would have a problem.
Well, I mean, you can factor this to 2 minus p, 2 plus p, but it's still under the square root. So you can't like do partial fractions or anything. You could use a trig sub.
Yeah, that's, yeah.
If you did a trig sub, you'd do a bunch of work and then you'd get
It's
this.
the same thing.
Yeah. So you can either just remember this or you can do all the trig sub stuff and then you'll get that as well. So it's just kind of a longer version of remembering that antiderivative. But you can do it that way. Any other questions on this one? Okay, I promised everybody that I would talk about Gabriel's horn a little bit, and that's worth talking about for sure. So let's do that really quick. And then I'll take another question or two if you have them. So first, let's look at the function f of x is just equal to 1 over x. The function looks like this. Okay, so it's just like a hyperbola. So just so we know what it looks like. And now the question is, first, let's say I'm here at 1, and I cut it at 1, and then I look at this, all of that area. Now, I want to say this in just a slightly different way. Let's say that I have this curve, and I have a can of paint, okay? And so I'm going to take my paint, and I'm going to dip my brush in the paint, and I'm going to start painting this curve. Now, how far out this way does it go? Yeah, forever. But let's say I had some time on my hands and I just wanted to start painting it forever. How much paint would it take? Now, hopefully we're experienced enough at this point to know that we shouldn't just say infinity, because we know that that could potentially converge, correct? And if it converges to a number, it would not take infinite paint. It's so tiny out here at the end that maybe it doesn't, but I don't know, maybe it would take infinite paint. Let's figure it out. So what I'm going to do is I'm going to calculate the area that I would need to paint. So the area would just be the integral from 1 to infinity of 1 over x dx. And we know how to do this. This is what we've been doing in the last homework. So this is the limit as b goes to infinity of integral from 1 to b of 1 over x dx, which is the limit b goes to infinity of antiderivative of 1 over x is ln of absolute value of x evaluated from 1 to b. So we get the limit as b goes to infinity of, we plug in ln, we plug in the b and we get ln of absolute value of b minus ln of absolute value of 1. Ln of 1 is just 0. So we just get the limit as b goes to infinity of ln of b. But ln of infinity is infinity. So I get infinity and this thing diverges. Okay, so what was my original question? It was, well, how much paint would it take to paint this curve if it just kept on going all the way out to infinity? In other words, in some sense, how much area is there for me to paint? And what's the answer? Infinite. Is everybody with me? So there's infinite area for me to paint on this. So now what I want to do is I'm going to say, okay, so infinite area. Let's take this same curve and I'm going to spin it around the x-axis. So cutting it right here, I spin it. And what shape would I get? Yeah, it kind of would look like, but it goes on forever, right? So it's this horn that like gets smaller and smaller and goes on infinitely far. So this is what we call Gabriel's horn. And now the question is, let's say I have this horn and I take it and I stand it up on its end so that like the top of the horn is right here. And then it goes, I look in the horn and it goes down infinitely far, right? So this horn, I'm looking into it, goes down. And so now I'm going to say, okay, I was interested in paint. So let's take some paint and I'm going to start filling the horn. Okay, so I'm going to pour paint into that horn. In other words, I want to know what's the volume of the horn. So I know how to do that because we know how to do rotations in each of these slices as a disk. So I just want to use the disk method, right? So the volume of Gabriel's horn would be equal to the integral from 1 to infinity of, the disk method is pi r squared. So I need a pi times r, and r is the functional value in this case, the height, which is just 1 over x. 1 over x squared dx. So this is pi r squared, disk method. Let's do it. I could rewrite, this is the limit, b goes to infinity, integral 1 to b of pi times 1 over x quantity squared dx. I could pull the pi outside the integral. In fact, I could pull it outside the limit if I wanted to, and I would get pi times the limit as b goes to infinity of, okay, so now I need to take the antiderivative of x to the negative 2. So that would be x to the negative 1 times negative 1. So negative x to the negative 1. So this would be negative 1 over x, or x to the negative 1, evaluated from 1 to b. Everybody buy that story? Okay, so let's plug it in. The pi's still there, the limit's still there. And now I plug it in and I get negative 1 over b, negative 1 over b, minus, plug in 1 and I get negative 1 over 1, so that's negative 1. Negative 1, okay? The pi's still there. And now I can take my limit. The limit as b goes to infinity, I get 1 over a very big number. 1 over a very big number is a very small number, so that's 0. So we get 0 plus 1. So I just get 1 times pi, or pi. Wait a second, that's weird. So what I just said is if I have this little strip that goes on infinitely far and I start painting it, it's going to take infinite paint, correct? But if I take that same shape, spin it around, I get a horn. I take my paint, I start filling it. How much paint do I need to pour? Pi cubic units of paint will fill it. But couldn't I take this strip and kind of like go and dip it in to the horn? Wouldn't it fit inside? It would fit inside, but yet this takes infinite paint. And that the horn takes finite paint to fill. So I think that what's so great about this Gabriel's horn situation is it shows you that you think you understand when it has to do with infinity, but oftentimes you do not. Okay, and I mean, the real cleverness of this is one of them uses kind of like a natural log, the other one it squares it, so now it converges, and it's just like right on the line in between convergence and divergence, so it works out. But this is just really a cool problem that kind of shows us that like when you're dealing with infinity, things get a little bit weird. Okay, and I think that in our mind, it's like, surely this one couldn't take infinite paint, and then this one fills with finite paint. It's pretty weird. So anyway, that's what it's called, the Gabriel's horn problem, and I like that one a lot. What's that?
Why does it do that?
There's no real like good why to it. There are things I have to say, but maybe it's best that I save it for when we talk about like infinite series in like the next chapter. I have some things that are interesting about this problem that I could say, but I don't think we're ready yet. Needless to say, for now, it's just weird. And it never goes away. Like, even if I did say more, it's still weird.
Yeah.
Like, how could you have something that has infinite area, spin it, and it has a finite volume? It's pretty weird. Yeah. So, kind of cool. Okay, so I'm done with my fun problem. Any other problems that you would like me to do? Yeah.
36.
36. Let's look at it. Okay, so 36, we have the integral from e squared to infinity of dx over x times ln of x raised to the p, where p is bigger than 1. All right. So first thing, what's the problem here? Like, what's the problem spot? So if I plugged in something like e squared, what gives me division by 0? Or why is this an improper integral?
Well, the infinity is.
Yeah, that's the only thing in this case. It could be that we have more than one problem, but the only problem here is infinity. So division by infinity is going to give me 0. That's not good in general. So yeah, the infinity is the only improper part of this integral. Okay, so we just need to rewrite as a limit. So we'll write this as the limit as b goes to infinity of integral from e squared to b of dx divided by x ln to the p of x. All right, so what I see here is we've got two things kind of going on. We've got ln of x to the p, and we've got 1 over x. But the derivative of ln of x is 1 over x, right? So that might be a really good u substitution. So let's substitute for ln of x and see what we get. So I'm going to say let's let u be ln x. So du is going to be 1 over x dx. So I rewrite this is the limit as b goes to infinity of the integral of, okay, the 1 over x dx becomes my du. And then I get 1 over ln of x to the p. ln of x is u, so it's just u to the p. So it's 1 over u to the p du. And if I wanted to, I could rewrite this using different limits of integration. If x is e squared, what is u? 2. Good. And if x is b, what's u? ln of b. So I'm integrating now from 2 to ln of b, and now I don't have to deal with x's anymore. This is where it's important, why they tell you that p is bigger than 1. Because if p was 1, this would be ln of u. But they're making sure that it's like, no. You just use the power rule. You don't have to worry about it being an ln. So this is u to the negative p. So if I'm taking u to the negative p, I raise the power by 1 and divide by the new power, correct? When I take that antiderivative. So I'm going to write this as limit b goes to infinity of, so it's u to the negative p. I bump the power up 1. So it's u to the negative p plus 1. U to the negative p plus 1, correct? And then I divide by the new power, which is negative p plus 1. So I divide by negative p plus 1, and I'm going to evaluate that from 2 to ln of b. And we're plugging in for u, right? P is just a constant number. I don't know, 3 or something, I don't know. But so just keep p as p. We're plugging in for the u. Okay, so when I do, I get limit b goes to infinity of if I plug in ln of b, then I get ln of b to the negative p plus 1. So I get ln of b to the power negative p plus 1. By the way, negative p plus 1, what can you tell me about that number? It's negative. And I think that that's important because it means it's actually on the bottom, right? If this is a negative exponent, and we know it is because p is bigger than 1, then this thing actually goes on the bottom. And maybe we should be writing it that way, but for right now, let's just leave it as is. And then on the bottom, I get divided by negative p plus 1. And then I plug in the 2, and I get minus 2 to the negative p plus 1, 2 to the negative p plus 1 over negative p plus 1. Close parenthesis. Okay, and why it's so important to remember that this it really lives on the bottom. Like, let's say that p was 3. Then this would be negative 2, and this would be ln of b squared on the bottom. Correct? Okay, so what's going on if b goes to infinity? So if b goes to infinity, ln of b goes to infinity, correct? So this thing's infinity. We've got infinity to a negative power. That means it goes on the bottom, which means that the bottom gets very, very big. And if the bottom gets very, very big, the fraction gets very, very tiny. So this thing goes to 0. Does everybody buy that story? This is easy to get messed up on. Like, if you really got to think this through and say, okay, I've got infinity here, ln of infinity is infinity. Infinity to a negative power is on the bottom, so it goes to 0. So this whole thing, I just like to draw an arrow through it and say that's all 0. And then what's left? All that's left over is, well, it depends on how you want to write this, but this is negative 2 to the, if you want to say it, you could say it's 1 minus p over 1 minus p. And if you wanted to put the negative in here, then you could say that it's 2 to the 1 minus p over p minus 1. So that works. There are a couple different ways we could write this, but that does it. Any question? Yeah.
Not on this one.
Oh.
On 45.
Okay. Any other questions on this one before I try something else? Yeah.
Could I write that 2 to the 1 minus p as 2, or 1 over 2 to the p minus 1?
Yes,
Okay.
you could. So if you put the 2 on the bottom, it's 2 to the p minus 1 times p minus 1. Yeah. So you could write the whole solution as 1 over 2 to the p minus 1 times p
And how
minus
you
1.
do that is you just factor out a negative to bring it to the bottom.
Correct. Yeah, you just multiply it by negative 1 to bring it to the bottom. That's right. Okay, you said 45?
Yeah.
Okay. $45. All right. So number 45 says we have the integral from 0 to 1 of x cubed divided by x to the fourth minus 1 dx. All right, and so the first question on this one is, what makes this integral improper? The 1 is bad, right? So the 1 creates a division by 0, and so we need to do something with that 1. Okay, so what we're going to do is let's take the limit as b goes to 1 from the left of the integral from 0 to b of x cubed divided by x to the fourth minus 1 dx. Okay, so now that we've taken care of the improper part, what is this, what's going on in this problem? What type of problem do you feel like it is? What's that? Yeah, we could do U substitution. Yeah, that works. That's probably better than what I was going to do. So that's, yeah, it's pretty easy with the U substitution. So if we did a U substitution, we have U is x to the fourth minus 1. du is 4x cubed dx. So we need a 4. So we need a 1/4. So I can put in my 4. And then over here, I can put in my 1/4. And now I don't even know if I need to do a U substitution, only if I really, really want to, because I have the derivative of the bottom is the top. And whenever the derivative of the bottom is the top, what type is it? It's a natural log. The natural log of the absolute value of the bottom, right? So this is just equal to, I've still got the 1/4 hanging out here. I've got the limit as b goes to 1 from the left of natural log ln of the absolute value of the bottom, x to the fourth minus 1, evaluated from 0 to b. Okay, if we plug things in, still have a 1/4, still have a limit as b goes to 1 from the left, and then I plug in my b, and I get ln of b to the fourth minus 1, ln of b to the fourth minus 1, and then minus plugging in 0, and I've got ln of absolute value of -1, which is 1, and ln of 1 is what? 0. So this is just 0. Okay, and now it's time to say, okay, what happens if b gets close to 1? If b gets close to 1, b to the fourth minus 1 gets close to what? 0. What is okay, this is really important. If I was taking something that was just really, really close to 1, not 1 itself, like 0.9999, and I take it to the fourth, it's like 0.99, whatever. It's a very close to 1. I subtract 1, I get a number that's very, very tiny and negative. But then I take its absolute value and it's very, very tiny and positive. Then what's ln of a very, very tiny positive number? It's negative, and it's very negative. What does ln look like? The natural log function looks like this, right? As it gets close to 0, it never is 0, right? There's no such thing as ln of 0. But if you get close to 0 from the positive side, it shoots down to negative infinity. So what's happening here is as b gets closer and closer to 1, this number gets closer and closer to being 0, but always positive. An ln of a positive number that's very, very tiny is very, very negative. So this thing becomes negative infinity. So I get 1/4 times, so to speak, negative infinity, which is negative infinity, and this thing diverges. Yeah.
Did you say approaching from the left side, not the right side?
It's B is going to 1 from the left side.
Right.
So, but when you raise it to the 4th, subtract 1, and then this is the most important part, and then take the absolute value, then I'm getting close to 0 from a positive side. Because this cannot be negative. Would you agree with me?
Yes.
So once I do this and take the absolute value, I get a positive.
Very small.
A very small positive, which is good because there's no such thing as ln of a negative number.
Okay.
Does that make sense?
Yeah.
So yeah, I get a very small positive number, which gives me a very, very negative number. And that's where we get our negative infinity from. Does that make sense? Yes, sir.
So it's called divergence when it goes to negative and positive?
Yes.
Okay.
Anything that doesn't go to a number like 3 diverges. Okay, so if it's a nice finite number, then we say it converges. If it's anything else, whether it be positive infinity, negative infinity, or it could just be like, like on the last homework, remember there was one where like you had to evaluate sine as x went to infinity. And it's like, it doesn't go anywhere. Like there's no such thing as sine of x as x goes to infinity. It does not exist, so it diverges. It doesn't diverge because it went to infinity or negative infinity. It just diverges because it doesn't go anywhere at all. Yeah.
So I was thinking about like, what if you had done a U sub before you had fixed the limit problem?
Yes.
And I think you would just get another limit problem from what I'm seeing.
So if you would have just done a U substitution, just left 1 in.
Yeah, and then if you would have gotten another limit problem because when you plug it in and you change the limits of immigration, you get 0 and then a limit from 0 to -1.
Yeah, you will still get the problem.
And then and then you can fix that.
Yeah. One thing, people asked the last time about, well, what if you just leave in 1? Right? Instead of taking the limit as b goes to 1 from the left, what if you had just left 1 in there? Then when you got here and you plugged in 1, what would you get? 0. And then you'd say, oh, ln of 0. And it's like, uh-oh, that's not good, right? So that's why, again, remembering that you're taking a limit is helpful because it's like, you're not actually plugging in 1. You're plugging in something very, very close to 1, which is actually, in this case, very different. And it's important, okay? So just keep that in mind that there is a reason why we put these limits in. Other questions? Okay, somebody online said one. They said 52. All right, so it's integral 0 to infinity of x e to the negative x dx.
Wait, what were you thinking of doing with this problem?
Oh, before it was, he said U substitution. That's so good and so easy. I was like, oh, we could do partial fractions. But then as soon as he said that, I was like, well, I don't want to do partial fractions if we can just do a simple U substitution. So sometimes that's the bad thing about having a lot of tools in your tool belt. Sometimes you're like, let's take out the very hard to use tool when you could just use a simple hammer to get the job done. But yeah, so it's good. Okay, so 52, let's look at that one real quick. So I have integral from 0 to infinity. This pen integral from 0 to infinity of x e to the negative x e to the negative x dx. Okay, so question, what's bad here? So really it's e to the negative x. That means that e to the x is on the bottom. E to the x is always positive, but if it got really, really big, then the bottom, would that be? Yeah, it's just the infinity, because anytime we're going out to infinity, we have to be careful. So we're not getting any real division by 0 here, which is something to always look out for. Okay, so I can just do my typical, take limit, b going to infinity, integral from 0 to b of x e to the minus x dx. And now what do you suggest as a strategy? Yeah, integration by parts seems very good. We want the x to get simpler. So let's let x be my u, which means that e to the negative x dx will be my dv. And so I want u to be x, and I want dv to be e to the minus x dx. du is dx, and v would be negative e to the negative x. So now we're ready to rewrite, and we get the limit as b goes to infinity of u times v. So I get x times negative e to the negative x, so minus x e to the minus x, evaluated from 0 to b, minus the integral from 0 to b of v times du. So that's negative e to the negative x times dx. The negative could be outside as a make that positive. So then I just have e to the negative x dx. Okay. Get this out of the way and come back over here. So now I have limit as b goes to infinity of, if I want to, I can go ahead and plug these in. I can plug in b for x, and I get negative b e to the negative b. By the way, just for fun here, since it's e to the negative b, I think I'm going to put the e on the bottom, and it's going to help me in just a minute. So I'm going to write this as negative b over e to the b, which is the same thing. Minus, if I plug in 0, I just get 0. Then I take the antiderivative of e to the negative x, and I get plus negative e to the negative x, evaluated from 0 to b. All right, so I get limit as b goes to infinity of, this one's pretty simple. I just have negative b over e to the b, negative b over e to the b. And then over here, I plug in b and I plug in 0, and I get plus, plugging in b, I get negative e to the negative b, or negative 1 over e to the b, would be another way of writing that. And then if I plug in 0, I get e to the 0, which is 1, but it's negative. So I have minus, when I plug this in, I get negative 1 minus 1. Did I close enough parentheses? I don't think I did. I think I missed the parentheses. Okay. And now I'm ready to plug in infinity for b. If I do, what happens here? I get 1 over e to the infinity, which is infinity. So 1 over infinity, this thing just goes to 0. What about here? This one I have to be a little bit more careful because it's infinity over infinity. But if I'm taking the limit as b goes to infinity of infinity over infinity, what do? L'Hopital's rule. That's right. So what I need to do is take the derivative of the top and the derivative of the bottom with respect to b. If I did that, then this, by the way, the limit as b goes to infinity of 1 is 1, right? So that one's done. I'll just have 1 at the end. But this other one, I get limit as b goes to infinity of the derivative of negative b with respect to b is negative 1. And the limit of e to the b with respect to b is e to the b. So now we have this limit, and then I still have that plus 1 at the end. So the limit now as b goes to infinity, e to the infinity is infinity. 1 over infinity is 0, and I'm left with 1. And that's it. So this is a great example of why, again, it's good to be taking the limit, because if I had just left infinity in, sometimes when you get here and you're plugging in infinity, you're like, and here I get infinity over infinity, and a really bad thing to say at that point is like, oh, and that's 1. You know, and of anything over itself is 1. So it's easy to make some sort of a silly mistake if you're not remembering, oh, I have infinity over infinity, so I need to use L'Hopital's rule. Sound good? Any other questions? Yeah.
46.
46. Okay. So 1 to infinity, cube root of x. Was it 46?
Yeah.
46, integral 0 to infinity.
Is 1.
1, okay, 1 to infinity of like dx over the cube root of x minus 1.
Yep.
Okay, so what's the problem here? Yeah, unfortunately, it's both of them, right? If you plug in 1, that's no good. If you plug in infinity, that's always not good. So we kind of need to split this thing. And the question is, so where do you split it? Well, it's really up to you. You could split it at 2, you could split it at 100. It doesn't really matter, but you do need to split it into 2 integrals because you don't want like 2 limits on the same integral if you can help it. Do you know what I mean? Like you don't want one limit going towards 1 and then another limit going towards infinity at the same time. It's just not a really good idea. Yeah.
Is there a problem that you could be given where you'd be forced to?
Oh, I'm sure that the answer to that is probably yes. It's not like we never want to take the limit of a limit, but it's just like for our own like sanity, we try not to. Okay, so yeah, certainly I could probably come up with something where you are forced to, but in this case, we're not forced to. So let's not do it. So what I would do is I'd just say, okay, let's choose 2 since it's a nice enough number. And I'll just rewrite this as the integral from 1 to 2 of dx over cube root of x minus 1 plus the integral from 2 to infinity of dx over cube root of x minus 1. And now this one can be written as a limit where we replace the 1. This one can be written as a limit where we replace the infinity. So maybe I'd rewrite like this. This is the limit as a goes to 1 from the right of the integral from a to 2 of dx over the cube root of x minus 1. And then over here, I have plus the limit as b goes to infinity of the integral from 2 to b of dx over the cube root of x minus 1. Now, here's a little pro tip. Don't use the same letter for both. Okay, it doesn't matter if you use A and B, but don't use A here and A here, or B in both places. It just gets messy. You can mess yourself up that way. So if you're using something for a lower bound and something for an upper, usually I'll use A as the low thing, the lower limit, and I'll use B as the upper limit. But it doesn't really matter what you use, just don't use the same, because that's confusing when you're taking two limits as the same variable approaches different things. It's like, that doesn't even really make any sense. So just be careful that you don't write that. At this point, I think it's just a U substitution.
Yeah, I was just confused on the setting up.
Yeah. So this makes, and it doesn't have to be 2. I just chose 2 because it seemed like a nice number. It could be 1001. The integration might not be as pretty, but you can do it. Okay? All right, I think that that's all the time we have for today. Just a review of what's coming up. Monday, we'll do a review for our second exam. That was the last section before our second exam. And then Wednesday, we will, well, I guess we have to, it's hard for me to remember that we have to break up our exam in 2 days. So I guess that Wednesday and Friday, we will take the exam. Okay, so I think we'll probably do it similar to last time. I think it was like A and C. I'll figure it out. I'll send something out and let everybody know who comes on which days. But either Wednesday or Friday of next week, you'll take exam 2. Okay, Monday will be reviewed. Have a good day. And
Okay, so I just need a bit of